Hi everyone, I'm Agnes, a dual doctoral student of University of Tartu, Estonia and Ben Gurion University of the Negev, Israel. I'm associated with the Center for Imaging and Processing in High Resolution, abbreviated as CIPHR, at University of Tartu. In this video, I and my team will present our recent research work on incoherent 3D imaging. Beam shaping is a well-established research area connecting computational, optical, and advanced manufacturing technologies. With beam shaping methods, it is possible to design phase masks that generate optical beams with a desired amplitude and phase distributions for a particular application. The application can be a common one, such as imaging, where it is sufficient to generate converging spherical wave. The application can also be unusual, such as optical trapping, where the exotic beams such as Laguerre Gaussian beams are used. In direct imaging mode, where an image of an object is recorded directly, only a diffractive lens is useful. The other beam shaping elements, such as the cubic phase mask that generate Yari beam and azimuthally varying diffractive lens that generate self-rotating beams, despite their exotic axial distributions, cannot be used for the imaging applications. This is because the exotic axial characteristics such as curved path in the propagation in case of a Yari beam and the rotating path in case of a self-rotating beam comes with the intensity distribution that is not suitable for imaging. What is needed for imaging is not least one focus point which is neither available in the Yari beam nor in self-rotating beam. The research problem is how to exploit the useful axial characteristics of the exotic beams for the imaging application. Okay, yes, there is a solution. There is more beam shaping calculations and more complicated diffractive elements imposing the challenges in fabrication.
At CIPHR Group, in collaboration with University of Latvia, we have developed a solution for the above problem. We have changed the mode of imaging from direct to indirect. What is indirect imaging? As the name suggests, it is not direct, it involves multiple steps: optical recording and computational reconstruction. The proposed indirect imaging mode changes the basis of imaging. In direct imaging mode, the fundamental building block is a point. Any object is composed of points. In direct imaging, object is sampled by a point. In indirect imaging mode, the fundamental building block can be anything, and the computational part always calculates the function with respect to the fundamental building block. So a strange pattern like this is a point in computational domain. This is like creating a new world of vision. This is incredible. By switching to indirect imaging mode, the axial characteristics of optical beams are preserved and transferred faithfully to the imaging system. The curved beam in direct imaging looks like this in indirect imaging mode. The self-rotating beam in direct imaging mode looks like this in indirect imaging mode. What can a scattering mask do? Just scatter light. In indirect mode, you can see that a scattering mask functions just like a lens. There are numerous computational methods for indirect imaging mode. In this study, we used the recently developed Lucy-Richardson-Rosen Algorithm.
This is the optical experimental setup that we used for our research work. The setup consists of two units, illumination unit and a recording unit. In the illumination unit, we use a high power light emitting diode from Thor Labs. After that, we have lenses to modulate and critically illuminate the object. Then we have the imaging unit. Light from the object is collimated using another lens and it enters the spatial light modulator, which modulates the light. And on the SLM, we display the phase mask and the intensity distribution is recorded by the image sensor. First we record PSF using a pinhole and then we replace the pinhole by the object and we record the intensity distribution. Then the PSF is recorded at different axial locations and the PSF library is created once. After that, the object can be recorded anywhere between the axial boundary and the 3D information of the object is reconstructed using Lucy-Richardson-Rosen Algorithm.
These are the reconstruction results for 3D imaging. We have recorded PSF and two objects at two planes. For diffractive lens, in the first plane, object number 3 is focused and other object information is blurred. In the second plane, the object number 1 is focused and other object information is blurred. We repeated the same for Axicon. Here, both objects 3 and 1 are focused for both planes. Also, When we look at the reconstruction results for the cubic face, the two objects are pushed away from one another than they are originally present. This shows the non-rectilinear propagation of light.
The indirect imaging mode is not just limited to transferring axial characteristics for imaging applications, but can also be used to de-blur images using synthetic PSFs. These are the colonoscopy images obtained from Dr. Scott, Laser and Piles Fistula Center, India. In this, row 1 is direct image and row 2 shows reconstruction results for Lucy-Richardson-Rosen algorithm. It can be seen that additional information is obtained from Lucy-Richardson-Rosen algorithm.
These are the experimental results of cone beam computer tomography for 4 objects obtained from Darshan Dental and Orthodontic Clinic, India. The first row shows the direct imaging of the object recorded by the tomography system. The second row shows the reconstruction results using Lucy-Richardson-Rosen algorithm. Comparing the reconstruction results using Lucy-Richardson-Rosen algorithm with the direct imaging, a significant improvement in contrast can be seen.
It is also possible to combine multiple beams and create hybrid imaging characteristics in indirect imaging mode. In the first case seen here, an airy beam and a self-rotating beam has been combined. Due to the pulling of characteristics towards one another, there is a reshaping of the axial distribution. In the second case, an airy beam and a random beam has been combined. Again, a reshaping of axial distribution is seen here. This research is joint work with University of Latvia, Dr. Scott Laser and Piles Fistula Center, and Darshan Dental and Orthodontic Clinic, India. We thank our advisors and collaborators, Professor Vijay Kumar Anand, Dr. Andhra Naresh Kumar Reddy, Professor Rasid A. Kani, Dr. Scott Aragya Singh, Dr. Millingtania.